see, a couple of things on the quiz maybe worth going over. So the first one, why does ice not form until, why does the frost cracking window start near -3 degrees C? And why does ice form first in the largest pores? It's because the freezing point is depressed in proportion to the curvature of the pore. That is, the smaller the pore, the lower the freezing point. So the freezing point in all of the rock is below 0 degrees C because it's all in pores. And then it forms in the largest pores because those have the least depression of the freezing point. And the fact that you then have liquid water everywhere else means that those pores have, the ice crystals forming in those large pores can draw on the water in the unfrozen surrounding pores. I think people did pretty well in part B. Let's see, part C. We're just dealing with the issue of time. So the question was essentially why do you get more frost cracking at some depth, relative to right at the surface, and that's because you get at some depth the daily fluctuations in temperature are dampened, and so you spend more time in the frost cracking window. And literally, all I was really looking for is, the figure shows that below this, at some depth below the surface, there's just more time in that window, as shown by the amount of stuff that's colored in. Part D, that was a tricky one for you, and that's not too awfully surprising to me, partly given the way it was worded and the confusion introduced by the fact that I used capital T both for time and temperature. Sorry about that. But yeah, so capital T, it's like I copied these things out of the book from various places without going back and thinking, oh geez, capital T here means time and there means temperature. Ah geez, oh well. Most of you figured that out, but so I guess you really had to know what you were doing there. So most people got that, the daily fluctuations are dampened out at about ½ a meter, and the annual fluctuations aren't dampened out until about 9½ meters deep. And what I wanted you to talk about a bit was, what does that tell me about where the maximum value is and where frost cracking reaches 0. So on the one hand, you've got the maximum frost cracking occurring at about the same place where the daily fluctuations go away. So that makes sense, right? If it's generally cold, you get maximum frost cracking where those daily swings that go above and below the frost cracking window are dampened out. However, because the average temperature of the year is above freezing, you still need substantial annual fluctuations in order to drive frost cracking. So the frost cracking shuts down at around 2 meters in this example, whereas the annual fluctuations drop out at a much greater depth. So that's really the key, is that your maximum frost cracking is associated with where the daily fluctuations are dampened out, but the annual are still large. You are far, far short of where the annual fluctuations finally drop off to insignificance. Because you've got to have that annual swing substantially in order to get you into the frost cracking window, because, unless you're in permafrost, right? If you're in permafrost, then forget about that. But if you're in a place where the average annual temperature is above freezing, then you need those annual swings. And then finally, number 2, I was looking for combinations of, well, what do we know versus what do we think is likely. We know that roots grow into cracks. We know that roots, trees when they're uprooted, bring rocks with them. So we know that at some point the rocks are broken. We don't know exactly when those rocks are broken. That is, are they broken when the it seems likely then, given that we do have evidence that wind transmits energy into the ground via the tree roots, that the rocks are being broken up prior to the tree actually being uprooted. It also seems likely, although it's a bit iffier, whether the simple turgor pressure, that is the sort of pressure exerted against the walls confining the root, simply that the tree can exert less than a megapascal in order to get water into the root. That's not a lot of pressure relative to the tensile strength of intact rock, but maybe it's enough. So that's where it becomes a bit speculative. We don't know, for example, whether that's enough to propagate cracks all by itself, or whether that simply serves to wedge the roots into the rock so that when the wind blows, you have higher friction, and the roots don't just slip easily in and out of those cracks, rather they pull and yank the rocks with them. Okay. Any questions?
So all we know for certain is that roots grow into cracks, and that when trees uproot, there are broken rocks in the roots?
Sort of. I mean, we do also have the data that show the seismic energy
Being transferred.
Being transferred by the wind, by the trees. The wind, we see the seismic energy due to the wind moving the trees and thereby shaking the ground. We don't know about the stresses that are generated precisely and whether those are, it's like if that breaks rock, then you would expect, then you would need to get seismic energy, and you do see the seismic energy. Eventually, when the trees fall over, you see the boulders embedded in the roots. So again, pretty likely that the rocks are getting broken up, but we don't have the bring it underground, right? So we don't have the direct observation. Again, science, for science, we got to be real careful about what exactly do we know versus evident, things that are consistent with evidence, but we haven't actually observed. Okay. Any other questions? All right. I want to talk today then more about chemical weathering, and again, I've got kind of an ambitious scope that I ideally like to cover. We'll see. See how far that gets. We kind of ended up last time. All right. Block and chew gum at the same time here. Not always productive. Okay. We ended up last time talking about the reactions, common weathering reactions, specifically hydrolysis, or that is AKA incongruent dissolution. That is where protons are swapped into the crystal lattice in exchange for mobile ions like calcium, sodium, magnesium, potassium. And then we also talked about oxidation, and specifically sort of ended up with, oxidation can result in the production of a fair amount of acid. You got a get a number of protons out the other end. And one of the things that sort of the upshot of where I want to get today, but I'll foreshadow it a bit, is that weathering is autocatalytic. There is a positive feedback mechanism in which, when you weather the rock, you produce more acid to weather the rock. So that's kind of interesting. But we do need to get into some stuff that's, I find a little less interesting than the gee whiz facts, because we do need to talk a bit about, okay, what's up with, we got to talk about we need a framework for analyzing the propensity for different reactions. In particular, we need to talk about equilibrium constants, solubility products, saturation indexes, and reaction rates. Okay. So I will start by writing up a general reaction general fake reaction, okay, which I will write thus and such. Okay, so these small letters here, these are the molar constants. That is, how many moles of compound B in this particular case. And then B there would be, of course, the compound. So we're talking little a moles of compound big A plus B moles of B as reactants, and on the product side, C moles of C, D moles of D. All right, we're going to define then the equilibrium constant. In terms of the activities and activities are, for the most part, at least for stuff that's in solution, equivalent to concentration. And also the stoichiometric coefficients. Okay, so let's come up here. Well, actually, let me give us a notation for activity. And again, we've got the activity of A is unfortunately A sub A. Or wait, did I get that right? No. A sub capital A. Okay. And again, most of the time, usually that's equal to the concentration of A, where concentration is denoted by the square brackets. Okay, and so activity is dimensionless. I mean, what are the units on concentration? The units on concentration are typically things like milligrams per liter. But that's actually sort of almost a fake unit, right? What that really means is parts per million. Which, again, that just means take that number and multiply it by 10 to the minus 6. And that's the dimensionless concentration. So for the general reaction, big K sub EQ for equilibrium is defined by, again, these activities. So we've got activities of the products raised to their stoichiometric constant exponents equal to their stoichiometric, I can't say that word. So that's the little c here, capital C here. Unfortunately, C is not a real good one for distinguishing, but it becomes a little more clear when I write the others out. Right, so we're talking activity of compound A raised to an exponent equal to the stoichiometric constant little a. Let's outline a few rules for doing this calculation, because this is all very fine if everything here is aqueous. Then yeah, it's all about concentrations. So what are the rules? If we're dealing with solute, that is stuff that's in the aqueous phase, then activity equals concentration. Okay. If the thing is solid, like calcite, solid calcite, or whatever mineral, then the activity is 1. If it is water, literally, actually H2O, the activity of H2O is always 1. And if we're dealing with a gas, such as CO2, carbon dioxide, or oxygen, then the activity is equal to the partial pressure. Yes?
The water, is that in any phase or only liquid?
Come on. Water that's frozen doesn't have solute. So I guess the technical answer is I don't know, because we're always dealing with stuff that's in liquid solution. You know, we're never dealing with, and I don't know if it's even a thing. Ice doesn't dissolve, so yeah.
It's not really between, I think it does work between the water, because it's pure water, and using the water vapor, which is a little gas, where we have solids, which is really
Yeah, that makes sense. So if you had water, like water vapor, then it would be partial pressure, not water vapor. Okay, yeah, that's a good point. Thank you, Michaela. All right. This isn't really a rule, but when we're talking about dissolution, then we call the equilibrium constant a solubility product. One way to think about why we might call it that is that, if the left-hand side of your reaction is all solid stuff and water, and the right-hand side is dissolved stuff, then your equilibrium constant is simply the product of the concentrations of the products on that right-hand side. Hence, it's no longer really a ratio, it's just a product, hence the term solubility product. Now that may not always, for some reactions, that doesn't necessarily hold, and we might still call it a solubility product, even though there's stuff in the denominator. But that's just it's just convention, what people call things. So let me just, quick give us an example. Let's write it under the general reaction over here. So for example, for gypsum, that is calcium sulfate in hydration with water. Hydrated calcium sulfate. And right, that's solid. And we're not even putting the water in there, but because you can kind of write reactions almost however you want. So the water doesn't really play into the reaction. So therefore, we just have calcium ions plus sulfate ions plus there might be supposed to be a 2 here, and therefore a 2 over there. Whatever. The important thing is, okay, then what's the equilibrium constant for this? Or so-called solubility product, we'll call it. It's simply the concentration of the calcium ions times the concentration of the sulfate ions. And I'm not sure I wrote this right. But in terms of the water, we could put that in there, but it's just 1. But if we wanted to be completely explicit about everything, okay, the activity of water, I'm going to put that in, but maybe just to remind myself that's the rule for water. But I don't have to unless I want to. Okay. Now, what if we're not in equilibrium? We can still, if I've got some reaction underway, okay, to erase this. I've got some reaction underway. It's not at equilibrium. What do I call the same? The quantity using those activities. Well, then I call it an activity product. Again, it has essentially the same definition or the same form as the the same form as the equilibrium constant, but these are the non-equilibrium activity. So Q then is the more general thing. In general, if these are equilibrium activities, then we'll call it KEQ. But we can still calculate Q whether these are equilibrium or not, and that means I can write, so I'm going to define. Or we can just look at the ratio, right? We can look at Q over KEQ or KSP, same thing essentially. But if that's 1, then that's equilibrium, of course, because then Q equals the equilibrium constant. If Q over KEQ is greater than 1, then that means we've got too much product relative to equilibrium. We're actually in supersaturation, and the reaction is driven left. Right? We're in the case, say, of gypsum, we're going to precipitate out. We're going to take calcium and sulfate ions in water, and we're going to precipitate out the gypsum. And then for the ratio less than 1, then that means the reaction is driven right. We're going to do more dissolution in this case. Now we, of course, can't just leave it at that, now can we? We're going to define saturation index . And we're going to define it in terms of the log base 10. And having the 10 here is kind of redundant notation, but just to be absolutely clear, of this ratio K over SP, written at SP here. The book does various things, goes back and forth between KSP and KEQ, and I think that's why my notes go back and forth between the two as well. But again, if we're dealing with saturation, then we are dealing with a solubility product. Q is a more general thing. And so that means, okay, if we go over here and we look at what's the log of something greater than 1? Well, the log of something greater than 1 is a positive number. So if this number is positive, then we drive the reaction to the left. If this number is negative, that means, well, the log of a number less than 1 is negative. So that means we're going to dissolve more. And so the more negative this number, in general, the faster the reaction. And let's actually quick look at that. So see that when so this is on this y-axis is the reaction rate relative to the sort of far from equilibrium reaction rate, R sub 0. And so far from when saturation index is large magnitude negative number, then this is 1. We are far from equilibrium. R equals R0. And when we get relatively close, but close is defined in terms of orders of magnitude, right? So -1 means we're at a tenth of the saturated concentration. -2 means that we're at 100th or 1% of the saturated concentration. So at only 1%, we have a modest but maybe measurable effect on the reaction rate. When we're at 10% of saturation, again, modest but perhaps measurable effect on the reaction rate. And as we get to smaller or closer and closer to 0, that reaction rate drops towards 0. And where it's 0, then the activity product is equal to the solubility product, and the log of 1 is 0, and so the reaction is essentially, well, it's not stopped, right, but going to the right equals going to the left. Do you have a question?
R over R naught is reaction rate?
R over R naught is the normalized reaction rate, so it's dimensionless, and it's simply saying, well, I'm going to define R0 as the reaction rate when I'm really far from equilibrium. So what we're just looking at is that as you get closer and closer to equilibrium, your actual reaction rate drops to a fraction of the far from equilibrium reaction rate. Okay, so at some point here we've got only, as we get very close to equilibrium concentration, we drop to say 10% of that nominal reaction rate. Okay. All right then. Now I can actually write up at least a decent equation for the reaction rate as a function of the saturation index. So for what it's worth, if the reaction rate is defined as the change in concentration with time of element I, so dCi would be a change in concentration of solute I, and dt is change in time, and that's our reaction rate. So a reaction rate would be, it would have a per time unit. And R varies with the saturation index as 10 to the SI, but that's just equal to so, in other words, what I just said with the graph, that if K plus is my forward rate constant, which has units of moles per meter squared second, then this is one expression for in terms of the original ratio of activity product to solubility product this away. Now, this is if, well, hold on. So if I've got some stuff sitting with water and it's doing its reaction thing and the water's not moving, then I'm just getting closer and closer to saturation, the reaction is slowing down because I'm not removing any of that product. But And that would be what we would call a transport limited weathering situation, which is maybe a little bit confusing because we already use transport limited to talk about erosion. But that is, so we might think of it as mobility limited. This would essentially apply to limitation by solute transport. However, most of the time that doesn't seem to be what limits the reaction rate. What seems to most of the time limit the reaction rate is actually the access to surface for reactions to take place at. So at least that's what we think. So if we break rock with physical processes, if we make more cracks and so on, then we would expect the reaction rate to be faster. In the case where we're not limited by solute transport away from the surface, right? So if the solute's not moving away from the surface, then we're going to get this sort of dependence as we get closer and closer to equilibrium, where the reaction is going to slow down. However, if the reactants or the reaction products are being transported away and the solution is moving, then we're not ever going to get towards equilibrium in this sense. Instead, the weathering rate, the rate at which the reaction takes place, is simply going to depend on how much surface the acidic water can come into contact with. Access to sites to put in protons and take out cations. All right. Now, it's worth, and the book does, and I think it is worth spending a bit of time thinking about, okay, what are the various things that do affect reaction rates? What are the dependencies? Anybody want to toss one out? Temperature, right. The faster, okay, hold on. Let me be clear. So in general, if we're talking about an aqueous reaction, the warmer it is, the faster the reaction. Now, of course, for solution of gas, it goes the other way. Because in order to get gas into solution, we want less energetic gas molecules to snatch out of the atmosphere. But for aqueous reactions, so for mineral theta, we have a reaction rate constant that varies as a function of temperature and activation energy. That should be an A, not looking like a Q. All crowded here, but. Degrees Kelvin, anyone? Okay. Sorry, ran out of room for the bin. And this, I spent a little time trying to figure out something a little bit more informative than something simply called the pre-exponential factor. And I guess I just have to live with that. All right, universal gas constant. So all that means is that I've got my reaction rate varies exponentially with temperature.
So is EXP a value, or is that just saying that it?
No, exponential. EXP is a mathematical function. Exponential. I could write e to the power of.
E to the power of negative EA over RT?
Exactly, yeah. Okay, so exponential of something in parentheses is equal to e to the thing in parentheses.
So the A has an exponent?
It's like the
Yeah.
letter E in math. That's what exponent is. It's E to the negative EA of RT.
I think it was people who like math and people who don't. If you like math, people use e to the something because it makes it a little bit clearer. But if you don't want to write out, if you don't want to deal with like putting stuff into superscripts and dealing with writing equations, then it's easier just to write x. And so the chemists do it this way, and physicists do it the other way, probably. That's my bias anyway. Is your bias showing? Okay. What else is the reaction rate dependent on? Come on, somebody, give me something.
The amount of stuff you have to take for reactions to take place. So like the
Well, yeah, but given that, yeah.
How about density?
Huh. I think we'd have to put that in with, well, that's actually an interesting one, and I was going to save it for later, but, I'll go ahead and write it up because you gave it to me. But rather than density, surface area. So as we get less dense, we might expect there to be more surface area in the middle. And this is kind of the biggie, really. Which is why we talk about reactions being surface limited. And again, there's an equation here. My reaction rate is equal to the surface area let me write this. Let me do this differently. So my reaction rate is going to equal the surface area of mineral theta over the fluid volume, that is the volume of fluid in contact with mineral theta, times the stoichiometric constant for element I in mineral theta and times the rate constant again, use that notation for theta. So that, I wrote all that out instead of the whole arrows thing. This is, I'm sorry, a bit less appealing looking, so you can rewrite that as a ace of theta over v times theta I theta k theta. Okay, everybody recognizes the lowercase Greek letter theta? Okay. Then that means that we got to do a good job of measuring a couple of things. We've got to, in order to know this volume, what do we need to know? It's not something we've talked a whole lot about, but we have talked a bit about porosity, right? The fraction of the solid that's not solid, whether it's filled with water or air. So we got to measure porosity. That's not so hard because, you know, we probably only want to consider the sort of drainable porosity, that is the part of the porosity that can act. You know, we could have isolated closed, you know, the difference between open cell foam and closed cell foam. We only want the open cells to talk about porosity here. That is the ones that waters can move among. And then measuring surface area of mineral in something potentially broken, something with a lower density as the mineral grains in it are worn away and we make bigger spaces, increase the porosity. Wow, I didn't get nearly as far as I thought I would. Well, anyway, so yeah. Now, next time I'll try to finish this up and actually talk about the interesting stuff that I really wanted to get to today, which has to do with a couple of things. You know, well, we didn't talk about pH dependence. That was sort of what I was fishing for as the next thing. But this other issue of, well, whenever we measure reaction rates in the lab, they come out like an order of magnitude greater than weathering rates measured in the field. What's up with that? And we'll start with that next time.